Hi students, welcome to my class. Okay, it's 3 o'clock exactly. So I hope you had a good lunch. Okay, actually what I plan to do today is to give you a few fundamental fundamental, or we call the fundamental lessons of chemistry, just to let you know what it feels to be in a science class in chemistry. Because I know a lot of you are not too sure whether you want to take up science or not. Some of you are still contemplating whether you want to go to science stream or art stream. So if you can follow the science, this lesson, and if you kind of like chemistry, so I suggest that you go for it. Okay, because science can be fun, can be interesting, and if you have a mind for it, I think you should go for science. Okay, because everything is going towards science and technology nowadays. So, okay, actually, I've had this lesson before with my 4 of my classes, or 3 of my classes, 3P5, 3P6, and 3P10. So some of the lessons are actually on my YouTube channel. Actually, this is the lesson that I had. This is the fundamental, the basic. This is chapter 2, but I did not record this. I did not put this on my channel last time. So I'm doing it again for the benefit of having it to be recorded so that it can be stays on my channel and anyone can go there and refer to it whenever they need to. Okay, so all right, so today I do not need you to give me attendance. All right, I do not need you to let me know who is here because I'm not taking attendance, so no need. All right. Okay, Lo Entong, yes. Hi, Kwan. Hi, Entong. All right, nice to have you here. Okay, so I will carry on going through the basic, right? The lesson will not last more than 1 hour, all right? Because I'll make it short and I'll give you all the important things that you need to remember. So if you have not followed my lesson, or if you're from other classes of Form 3, so I suggest you go through this lesson first, and then later on you can continue with all the other lessons that I've had with 3P6 and 3P10, which I've recorded. Okay, only me. I do not know, Entong. Maybe the other girls don't need a revision because I've had a lesson with you before, right? 3P10, right? Yeah, 3P10. So maybe what I'm doing is for the benefit of the other girls or the other classes who may need to know this, especially 3P4, right? 3P4 did not. I started off with science. Art science for them, so I did not go to chemistry. So I think there are a few girls who told me in that class who want to do chemistry or want to go to science class. So I think coming to this lesson, have a feel of chemistry, that will be able to let them know whether they want to do science or not. Okay, Alisa, hello. Okay, Sarania, hello. Gopala, Krishnan, hi. Nice to meet you. All right, okay, let's start. All right. So first thing, this is actually what you have learned in Form 3. Okay. You know this is the atomic model. This is the atom, right? In the atom, what is defined as an atom? The atom is the smallest unit, okay, which is indivisible. That means you cannot divide into smaller units after the atom. It means there's nothing else smaller than atom. But of course, inside the atom, there are actually what we call subatomic particles. So we say if you have the smallest unit, okay, that make up matter. If the question asks you what's the smallest unit that makes up matter, it should be atom. Okay, but in the atom itself, there are actually smaller units that make up the atom. They call it the subatomic particles. Okay, you have learned it in Form 1 before, actually. All right, so let's go through this. All right, now let's learn in a bit of detail, right? Okay, we have the proton. You learned this before, the proton. And you have the neutron and the electron. Okay, so remember this: P, E, and N. All right, remember your pen, right? So in the nucleus, this is actually the core. The nucleus has proton and neutron. Proton is symbol, they use a symbol P. Neutron is symbol N. Okay, proton has positive charge, positive 1, and neutron has no charge at all, so it is neutral, right? And it makes the nucleus positive charge because of the proton. The mass of proton. Now, what is the mass of proton? It is, of course, very, very light. Okay, it's very, very light. So we cannot actually put a figure to there is, but it's very difficult to remember because the number will be very, very messy. Okay, something point something times 10 to the power of negative something. So it'll be many, many, many zeros behind it. So in order to make things easy, so we want to compare the mass of proton, neutron, and electron. So we want to put it as like this, right? We call it an arbitrary unit. So proton is just considered as 1. Right, so proton, the mass is considered as 1. So we compare proton against other subatomic particles just based on 1. Okay, so if it's 1, then neutron is also 1. That means equal weight or equal mass. So the mass of neutron is actually the same as the mass of proton. All right, so we just have the unit 1. All right, relative mass, you don't have a unit behind that, just say 1. Okay, means same. Proton and neutron has the same mass. Okay, if we compare electron, sorry, I've written it wrongly here. All right, here this should be N, this should be E. All right. Okay, so are you able to see the screen? I think no problem, right? I think I'm looking at it, right? So no problem here. Okay, are you able to hear me? Can I have some response from the students here? I think, am I able to, are you able to hear me well? Okay, and see the screen as well. See my PowerPoint, see my share screen here. Is it all right? Can I have a response? Maybe yes, if everything is okay, then I can continue. Okay, I'm checking it. Yeah, I think everything is fine. Okay, I'm able to, yeah, all right. Okay, thank you for your response. Okay, so let's continue. All right, now let's talk about electron. Electron is actually very, very, very light. Okay, it is about how light is it? It's very, very much lighter compared to your proton and neutron. So the charge is negative, so it's negatively charged, and the mass, relative mass of it is about 1/1840. That means, what does it mean? Okay, it means it is 1,840 times lighter compared to proton. Okay, which also means you need 1,840 electrons to equal the mass of 1 proton. Okay, that is what it actually means. So 1/1840, it is the mass of electron. And you can see the electron, they are actually orbiting around the nucleus, all right? And it's actually much further than this model shown here. So this electron actually is very much further away. So it's like a cloud of electrons, okay? Orbiting, and moving around the nucleus. So this is what you already know, all right, from Form 1, okay, when you learn about the model of the atom. Okay, but we have to go a little bit more, right? Later on, I'm going to see other concepts that you need to learn in Form 4 chemistry. Okay, so, right, let me go on, right? Now, who came up with this model, right? Who says that the atom should look like this? Right? This atom should look like this. Okay, so if we look at the history of the development of the atomic model, okay, there were a few scientists who actually thought of the concept called atom, right? Actually, the word atom came many hundreds of years before, right? This is around 500 BC when you have a Greek philosopher, Democritus, who said that there was such thing called an atom, right? But actually, if we talk about modern science, okay, we attribute the model atom to the first one, to this scientist called John Dalton. So John Dalton mentioned that when we talk about atom, it is the smallest unit of matter, which is indivisible. It's the smallest unit that makes up matter. It is indivisible, that you cannot divide into smaller units. Okay, it cannot be created nor destroyed or divided any further. Okay, and he says that it's just like a ball. All right, he doesn't talk about any of the charges that we know of. He didn't talk about the proton, the neutron, or the electron. He just said that it's just a round little sphere, right? Just a sphere. And he said that if element A and element B, right, if they have the same atom, then it means that they are the same elements. Okay, there's a question here, I see. Okay. Yeah, yes, let me check. Let me show your question, right? So, okay, Lo Entong, you may ask, if 1,840 electrons equal to 1 proton, so 1,840 electrons also equal to 1 neutron? Yes, correct. That's right. Because proton and neutron have the same mass. Okay, so you can also say that. All right. Okay, let me go on. Now, let's talk about, okay, so this theory, or Dalton's theory, went on for about a certain time, all right? Then later on, we have other investigations, others research done by other scientists. So one of the notable ones was Thomson. So Thomson said that actually there's more than to just the spherical ball called the atom, okay? He said that inside the atom, all right, the whole thing is positively charged. The atom is positively charged, but you have what we call electrons, which are embedded, okay? Embedded, that means they are actually like stuck inside here. So he mentioned that electrons are embedded in the neutron. Okay, so that was his theory. He said that this thing that Dalton said is not as simple as just having a ball, right? You have electrons which are stuck on the sphere, all right? And it's not like the model that we know. It doesn't circle, right? He says it's just stuck there. It's just stuck on the sphere itself. Okay, that was Thomson's theory. Then later on, he found that this is not actually 100% accurate. Okay, there are other scientists who actually built on that model. Okay, he said that, all right, true, there are electrons, right, and the atom is positively charged, all right, but let's see, all right, next scientist says Rutherford, all right, this is Ernest Rutherford. He says that nucleus is the center, so this is what he mentioned, and there are positively charged particles called proton. So observe earlier on that Thomson did not call them protons. He just mentioned that atom is positively charged, but he didn't say it's called protons, all right? But Ernest Rutherford said these are positively charged particles which are inside the nucleus, and they're called proton, all right? And then there are electrons, but these electrons are not embedded inside. They are not embedded in the nucleus itself, but they move outside the nucleus. Okay, so this is Rutherford's theory. All right, so later on, even more other scientists actually built onto this concept. All right, we have Niels Bohr, who mentioned that actually the electrons are orbiting. Orbiting, that means it's like a planet, you know, like our solar system. You have the sun here, and you have the, the planets orbiting around it. So you have these electrons orbiting around them, and this orbit is called shells. Okay, so later on they found there are more than one shell, not just one shell, right, orbiting around the nucleus. And you have in the nucleus, you have protons, right? So this is basically about the same. Only thing that Niels Bohr said that they are shells. These electrons actually orbit around the in certain pattern, right? Call them shells around the nucleus. And then next one we have James Chadwick, who also built onto this model by saying that, all right, there's not only protons inside there, there's something else called neutrons, right? So there's something else there called neutrons, and these neutrons are not charged. So neutrons and protons are the ones that are in the nucleus with the electrons circulating and orbiting outside, okay? And most of the mass of the atom come from the nucleus itself. That means the electrons are actually very, very, very light. All right, okay, so this is what the scientists have come up with. At the moment, we are actually following the concept of the theory of atom based on the latest one, which is James Chadwick. All right, okay, so of course there will be other atomic theory and also models, but we'll follow the latest one, okay? There will be others as well. Okay, so these are the 5 names that you need to remember. So let's look at it again. First, we start with Dalton. All right, Dalton, and then Thomson, then you have Rutherford, then Bohr, Niels Bohr, and Chadwick. Okay, you will see some of these names inside. In fact, in your periodic table of elements, you have borium. There's an element called to name this person. All right, it's taken from this name of Bohr. We call it borium. Then you have Rutherfordium. Okay, given in honor of Rutherford. So you have this element called Rutherfordium. Okay, so do you have any questions? If not, then we can proceed to the next part. Okay, just wait for a few seconds for any response from any of you. Okay, so there are some questions here. All right, but I think you can actually do it in your own time, all right? So this, you can take a screenshot. If you want to try out the questions here, take a screenshot and try it out in your own time, okay? Now we go on to a very important concept called about protons number and nucleon number, okay? So you always need to remember this. Okay, proton number and nucleon number. What are proton number and nucleon? Every element has got a proton number and nucleon number. It's like an identification for the element. Okay, now look at these 3 elements here. Okay, you have oxygen, sodium, and chlorine. Okay, I'll switch to full screen. Right, oxygen, sodium, and chlorine. Now, each one of them will have a specified number of protons in the nucleus. So for example, oxygen has got 8 protons, okay, and it has got 8 neutrons. So if I were to draw it, let's look at oxygen. If I were to draw it, okay, now look at this picture here. There will be 8 new protons, which I've labeled as white color. And for 8 neutrons, these are the black ones. All right, so you have 8 protons and 8 neutrons. All right, so that makes a total of 16, correct? 8 neutrons plus 8 proton, you have a total of 16. Now this number 16 is called nucleon number. Okay, so nucleon number actually refers to the total number of protons and neutrons in an atom, all right, or in the nucleus. So remember clearly here, nucleon number, not neutron. So please do not make the mistake. It's not neutron number. Not neutron number. It is nucleon. Nucleon number is actually the number of proton plus the number of neutrons. So 16 is the nucleon number. Okay, so you can observe here, 8 plus 8 here, right? You plus these two, you will get nucleon number of 16. And what is proton number? Proton number is actually very easy. It actually refers to the number of proton. So if your number of proton is 8, that means your proton number will also be 8. Okay, right. Now let's look at next one, sodium. Sodium is another element. All right, now how do we know it's a different element? The reason is because it has a different number of protons. Okay, so every element has a fixed number of proton. So the number of proton is like a proton number is like the identification card for an element. Okay, whatever the element is, it is based on actually how many proton it has. So if they have the same number of proton, they should be the same element. All right, that is what that's what it means. If you have the same number of proton, right? Let's say element A has number of proton of 7, then element B has a number of proton of 7. That basically means that both of them actually are the same element. They are not different elements. Okay, now, so here, let's look at sodium. Sodium has a number of protons 11, right? And so happen to be the number of neutrons is 12. So they may not equal, right? The number of protons and number of neutrons, usually they do not equal. This one for oxygen, they happen to be the same. But usually neutron, if there could be more or there could be less, all right, depending on the element itself. So it's not fixed, right? But proton is always fixed for the element. So that means oxygen will always have 8 proton. Sodium will always have 11. Chlorine will always have 17. All right, okay? So now, for sodium, the number of proton is, the proton number will be 11, all right? Basically because the number of proton is 11, so proton number is 11. And the nucleon number will be 23 because you have to add these two. Okay, proton plus neutron will give you the nucleon number. So this is something very simple. Okay, let's look at another example. So chlorine, 17 proton. So that means the proton number is 17. And so happen the neutron number, the number of neutron is 18. So if you add these two, you get 35. 35 is the nucleon number. Okay, so there's a formula here that you need to remember. Right? Nucleon number actually equals to the proton number plus the number of neutrons, or we call it the number of proton plus the number of neutrons. Okay, so if I give you any of them, if I give you nucleon number and I give you proton number, you should be able to find the neutron number. All right, okay, let's look at a simple example lah. Right, simple example. Okay, look at example 1. I won't show you the answer here. Okay, an aluminium atom has 13 protons and 40 neutrons. All right, so what are the proton number and nucleon number of aluminium atom? So aluminium number has 13, aluminium atom has 13 proton. That means this is a proton number. The proton number is 13. Okay, and it has 40 neutrons. So they ask you what is the proton number? They already answered. Okay, proton number is 13. You just look at the number of proton. And nucleon number, okay, how to find the nucleon number? So nucleon number is again very simple. You just take your proton, how many proton, you plus your how many neutron, you will get your nucleon number. Okay, and so the answer is, so you got to plus this one and this one. Proton plus neutron, you will get nucleon number, 27. Okay, so it's very simple at the moment, right? Yeah. So this is a basic concept, right? Same, if I give you the nucleon number, for example, example number 2, if I give you the nucleon number 39, and I give you the proton, it has 19 protons, you should be able to tell me how many neutrons there are, correct? Okay, so because your nucleon is already proton plus neutron, and proton is 19, so that means your neutron should be how much? 39 minus 19, that should be 20 neutrons. Okay, 20 neutrons. You just take your nucleon number and you minus the proton number. Okay, then how many electrons are there? Okay, you've answered the first answer, the first question, neutrons. Now, what about electrons? How many electrons? Okay, now electrons should be the same as the number of protons. Because when we talk about atoms, the atoms are always neutral. Okay, when they are neutral, that means the number of protons will always have to equal the number of electrons. All right, so they should be the same. That's why it is neutral. So the number of charges will equal, number of positive charges will be equal to the number of negative charges. So your answer here, electrons will be same as the number of protons, which is 19. And for the neutrons, you take your 39 minus 19, you will get 20. Okay, so 20 is the number of neutrons. Yes, right. Okay, yeah, Antong, you're right. Okay, 39 minus 19, you get 20 neutrons. Correct. Okay, so this is very basic. All right, just have to remind yourself how to get the number. All right. Now, when it comes to ions, okay, now let's talk about ions. I'm not sure whether you've learned ion before. Ion is actually charged atom. Okay, let's talk about ions. So atoms, like I said, is always neutral, but sometimes your atom can be charged. Your atom can be charged is because the electrons can be donated, or the electrons can come in. New electrons can come into the atom. Okay, so atom is always charged. Atom is always neutral, like I mentioned. But sometimes your atom gets to lose electron because of chemical reaction. Okay, or sometimes it receives new electron. In that case, your number of proton and your number of electron will not be the same anymore. Okay, so now let's look at here. Now, chlorine atom. Let's look at an example. Chlorine atom. Chlorine atom has got 17 protons. Okay, so I'm not going to draw 17. There'll be way too many in the nucleus. And it tells you there are 18 neutron. All right, 17 proton, 18 neutron. That means what is the nucleon number for chlorine? Would you know? Can you calculate what is the number of, what is the neutron number, a nucleon number of chlorine? Would you be able to find it? What's the nucleon number? Nucleon number is actually proton plus, proton plus neutron, which is, you add these two, you will get 35. Okay, that is the nucleon number of chlorine. All right, okay. Now, electron is the same for proton because they are atom. It is neutral, right? Proton, number of protons same as number of electron. But you see, for an ion, it's different. All right, you have 17 protons. You see, proton never changes. All right, yeah, correct. Entong, your 35 nucleon number is correct. Okay, for proton, it never changes because it is basically the same thing. If it's chlorine, whether it's atom, it is ion, it's still 17 proton. So proton number doesn't change. And it's, like I said, this is the identification for a element. Rather, it is whether it's atom or it's element, whether it's atom or ion, it should never change, right? The proton number should never change. Neutron also can actually change or doesn't change. It depends on the different type. We'll look at it later, isotope, we call it. Now, but look at the electron here. Earlier on, our atom has got equal number of proton and electron. But now you see you got 18. Now, how did it happen? How do you get 18 electrons? Okay, it is because sometimes the atom can accept electron. Okay, electron can come in. A new electron from another element, donated from another element, and it comes into this atom. So it receives an extra electron. So it becomes 18. 18 electrons. Okay, 18 electrons. That means the charge is no longer balanced. Am I right? Okay, so if it's no longer balanced, let's see, it has an extra electron, extra negative charge. So what you can see here is, right, now, the electrons are actually put in different shells. So if you haven't learned this, this is something new for you. If I want to draw the electrons around the nucleus of chlorine, I'm taking an example of chlorine. Okay, let's look at chlorine. Chlorine, basically, it has 17 electrons. Let's draw the atom first. Let's look at the atom first. All right, basically, it has 17 electrons, but 17, they are not all together. They're not all together. They actually exist on more than one orbit or the shell. Okay, so you need to remember that the first orbit is this one. Okay, let me draw again. Let me just drop everything and I'll draw it again. Right, so this is your proton, 17 proton with 18 nucleon, neutron in the nucleus, right? So the first shell can only fit 2 electrons. Can only fit 2 electrons, okay, not more. So if it's only fit 2 electrons, so you have altogether 17 to fit inside here, right? So you are left with 15. All right, so the 15 must go somewhere else. Where must it go? It should go on another shell, the second shell. Okay, but the second shell, unfortunately, also cannot fit 15. The second shell, maximum can only fit 8. So I'm drawing them 2 by 2, so it's easier for you to count, to see. So 2 is already 4, 5, 6, 7, 8. So there are 8 electrons in the second shell. Okay, so we have actually used up 2 plus 8, 10, right? So we have now how many more? So we have actually taken 2, we have taken another 8, so it's 10. We have 7 more to go because the total is 17. Okay, so the extra 17 has to go onto the third shell. It cannot fit into the second shell. It has to be on third shell. Okay, so let's draw the third one. Third shell, 1, 2, 3, 4, 5, 6, and 7. Okay, so this is 7. So the arrangement, we call this the electron arrangement, is 287. This is how you want to write the electron arrangement. If the question asks you, write the electron arrangement for chlorine atom. Okay, so first of all, you need to know there are 17 electrons. So you got to fit them into different shells. So it's 2, 8, and 7. So the last one is 7. All right, so altogether will be 17 electrons. All right, now, so you see here, sometimes chemical reactions happen and electrons can get to be transferred from one element to another element during your chemical reaction. So happened that this chlorine atom, sometimes it can receive electrons. Okay, actually it's easier to receive electrons than to donate electrons. Okay, so in this aspect, you see that actually a new electron has come inside. Another electron has come inside here. So now it has become 288. Okay, now this is no longer an atom. All right, now why I say no longer an atom? The reason here is because earlier on we had 17 proton, which means 17 positive charges. Now you have 18 electrons. Okay, so the charges do not balance. You have an extra negative charge. Okay, an extra negative charge. So we call it an extra negative charge. So now this particle is no longer neutral. It's actually negatively charged. And then we do not call it atom anymore. We got to give it a different name. We call it an ion. Okay, so how would you draw an ion now? So the ion would have like this. All right, I have to draw it here. You will have to have, of course, inside here is still the same. You have 17 protons, all right, and also 18 neutrons. Nothing happens inside, right? It's always outside because the electrons are there. Electrons are able to move away from the orbit. Okay, 1 here, 2 here. All right, wait. All right, 3, 4, 5, 6. Okay, now here, this is the second shell. So now the third shell, you have 8 already. So 1, 2, 3, 4, 5, 6, 7, 8. Now this is the new one, which is 8. So you have an extra one, an extra electron. So this is called a chloride ion. Okay, how would you draw it? You actually draw like this, and then you put a bracket here, a square bracket here with a negative charge here. Okay, there's a question here from, there's a question here from Entong. The number of electrons in ion must more one than the number of electrons in atom, teacher. Not necessarily. It can be more, sometimes two. It can be not always one. It can be, it's not fixed. And depending on whether it receive one electron or receive two electron or even three electrons, depending on the chemical reaction. Okay, and depending on actually the we call it the characteristic of the element itself. Some is easier to, some prefer to receive one. Okay, later on we will see why. It's because we want to, it wants to achieve the stable octave. The stable condition here is every orbit is either you need to have 2 or 8 or 18. Because you see, in this octave, we call it this is what we call the shell. 2 is the most stable. You cannot have 3, okay? You cannot have 4. So if you want to have 4, you must achieve 8. Then only considered stable. 8 is also stable, okay? If another shell, let's say bigger shell, is 18. Now, if you want to make it stable, you got to achieve 18. So depending on the element itself. So in this case, why the 7? Just now the last shell is 7, right? Why it received an extra one? Because it wants to become stable. Whenever you form a configuration of 8 electrons, it's considered very stable. We call it octet arrangement. Octet means 8. Okay? Or if it's 2, we call it a duplet. So either 2 or 8 is very stable. So this atom always like to get 2 or 8 in the shell. Every shell, you always try to achieve 2 or 8. So just now we had 7. Okay, 7 is because it's short of 1 to get stable, to become stable, right? So might as well receive 1 lah. So you will get an extra electron come inside, and then you will have a very stable kind of the last shell. Okay, so this is why it becomes an ion. So even if it forms an ion, you will see that nothing happens to the number of proton, nothing also changes to the number of neutron. It's only the electron that changes. So that means your ion and your atom should have the same number of proton. It should also have the same number of neutron. All right, okay? Now, when an ion is formed, all right, it becomes either positively charged or negatively charged. Now, just now we saw this chloride, right? Chlorine. If it's negatively charged, we call it an anion. This ion is called, an anion is a negatively charged ion. Okay? If it's negative, so happen chlorine is negatively charged because it received 1 extra electron. So it becomes negatively charged. So it is called an anion. So if example question asks you, give me example of an anion, you can say chloride atom, as chloride ion. Okay. On the reverse, if you have a ion which is positively charged, okay, it's called a cation. Okay, now how to remember this? Always remember the word cat has a T here, so it looks like a cross, so it looks like a positive charge. Okay, now how does something become positively charged? So just now you say how to become negatively charged, you have to add an additional electron, right? So it becomes negatively charged. But if you want to become positively charged, you have to throw away extra electron. That's called donating electron. So when an atom donates electron, it will become positively charged. Okay, I'm gonna give you an example. Maybe I can give you an example, then you can see better. All right, let's say sodium. Right, sodium is this 11 protons, and it has actually 12 neutrons here. Right, this is a sodium. So you have how many? You have 11 electrons to fit. Because there's 11 protons, it must have 11 electrons. So how to fit into the shell? Okay, let's draw it now. First shell, you need to fit 2 only. You can't fit more. Just now I draw the needle wrong here just now. I know. Okay, 2. First shell, you can only put maximum of 2. Okay, second shell. How many you can put? 11 electron, you've already taken 2. So you need to fit how many more? You need to fit 9 more. Right? But the 9 more cannot fit into the second altogether because the second, this shell maximum, how many I mentioned just now? You should have only 8. So 8 goes into here, the second shell. All right, so 9, all right, already you have used up, you have already fit 8. You need to fit one more electron, right? One more electron fit where? You cannot fit into the second shell, it has to go into the third shell already. So this is one more here. This is, so what is the electron arrangement? Can you try to write the electron arrangement for sodium atom? Anyone who's watching now, okay, try to write into the comment or the chat box there. What is the electron arrangement for sodium atom? Okay, how would you write it? It has a number with a dot here and a number and a dot here and a number. So, do I have any response? So, first shell, how many? Okay, let me try to help you a little bit. 2, right? What about the second shell? Second shell fits how many? Second shell fits 8. Correct? Yeah. And the third shell fits 1. So the electron arrangement of sodium atom is 281. Okay, now so 281, you see the third shell has got 1. Okay, let me highlight this. Now having 1 here, is it stable or not? In order to be stable, it has to be either 2 or 8. So 1 is not stable, right? In fact, 2 is only for the first shell. For the other shells, actually, it should be 8. So in order to it to be, the last shell has to be 8. So here, either there are 2 ways it can become stable. Either it has 2 methods. One is either you donate it away so that you're only left with the second shell with 8, or it has to receive 7. Correct? If receives 7, then the last shell become 8 lah, right? So either it donates 1 electron or it receives 7 electron. Yeah. All right, Elisa, you are right. Yes. Elisa, yes, correct. You're right, huh? All right, correct. 281. So, which is easier, do you think? Is it easier to donate 1 or is it easier to receive 7? Which one would the atom prefer to do? Donate 1 or receive 7? Do the easier one, isn't it? Do the easier one, which is donate 1. Yeah. So 1 is easier for the atom to just donate and throw away your 1 than to receive 7. Okay, it involves a lot of energy, right? So 1 is donated. So when 1 is donated, it prefers to do that way. In fact, it happens all the time for sodium. Sodium prefers to donate 1 electron than to receive 7. So it's easier to do it. Okay, so once it donates your 1 electron, let's look at what's going to happen. How does it look like now? How does it look like now? It looks like, okay, I'm going to draw this a little bit further. Okay, so inside here, no change, remember? When a proton receives or becomes an ion, there's no change to the proton or the neutron. Nothing happens inside here. It's only all the outside. So now here, there's no change. The first shell, 2. Second shell is 8. And the third shell has gone already, right? There's no other third shell, so we don't need to draw it. So now the last shell is 8. We have called an octet. This is very stable. So now it has less 1 electron. That means the arrangement is now 2-8 only. Very stable. But we cannot call it an atom anymore. Because now, why is it no longer, why it cannot call an atom? Look at the number of charges here. You have 11 proton, right? 11 proton now. 11 positive charges. You threw away 1 electron, that means you got only 10 electron now. Correct or not? So, it has got 11 positive charges. It has got 10 negative charges. So that means it's unbalanced. You have an extra of positive charge. Okay, so there is a positive charge extra here. So you will see here, if you donate electrons, it tends to become a positively charged ion. Okay, when you donate electrons away, it will become positively charged. And then if you receive electron like just now, like the chlorine, if you receive electrons, it will become a negatively charged ion. Okay, so you see the difference here, right? So in order to form a positively charged ion, or we call cation, it has to donate electrons. All right, okay? In other words, it doesn't make any difference to your proton number or your nucleon number, sorry, okay? So, any questions so far here on the formation of ions? Okay, we've seen the formation of ion, we have seen the number of neutron, the nucleon number and the proton number. Okay, next, let's look at the standard representation of an atom. How do you write the element, right? The symbol of the element. Okay, every element has a symbol which is already fixed. Okay, everybody must follow. For example, carbon is always C, calcium is Ca. Okay, nitrogen is N, oxygen is O. This is all fixed. And here you will see two important numbers. The one on top is the nucleon number, which is always bigger than your proton number, which is at the bottom. Okay, so nucleon number, remember, is proton plus neutron. Okay, it will always be higher, or the number will always be bigger than your proton. It can never be smaller because your nucleon number includes your neutron as well. So there's going to be definitely bigger number than your proton number. Okay, so let's look at C12. What does C12 mean? C12 means this is the nucleon number. 6 at the bottom here is the proton. So are you able to find the number of neutron there? If I give you this C12, 6 like that, you're able to find the number of nucleon or not? A number of neutron or not? It's very easy, right? You take this number, you take the top number, you minus the number at the bottom, you will get your neutron number, a number of neutron, okay, which is 6. Okay, same thing for sodium. Sodium, we have 23 and 11. So if I ask you what is the number of neutron, the number of neutron is, you take this number, which is 23, you minus 11, you will have 12. So 12 is the number of neutron there. See, okay? All right, okay, so this is basic, right? You need to know all this. Okay, and this is another exercise which you should try out. All right, so you take a picture. I think some of the classes I have gone through this. I have gone through some of the questions. I'm not sure whether I've done through all or not. So you can try and understand your concept. Try to remember it. Okay, do the exercises here. Okay, let's look at the arrangement. Okay, I've gone through this just now. So let me arrange, let me go through it again in detail here. So the electrons of an atom orbit around nucleus now in their respective shells again here. So if you're not too sure what I mentioned just now, this is actually what I've already skipped ahead. I've gone through ahead a little bit. And actually I'm supposed to tell you here now. All right. First shell maximum can fit 2 electrons. Second shell maximum of 8. The third shell maximum of 8 electrons. But if your proton number of this element is more than 20, the third shell can fit maximum of 18. Okay, so that means if your number of proton is more than 20, that means more than the after calcium. Calcium number is 20, the proton number is 20. All the elements after calcium, right, in your periodic table of elements, the third shell can fit 18. Okay, so if it's the proton number less than 20, it will only fit 8 only. If more than 20, the proton number, it can fit 18 on the third shell. All right, okay, so aluminium. So how do you write the proton arrangement of aluminium? So the number of proton, first of all, look at number of proton. Number of proton means the number of electrons will be the same, 13 electron. You try to draw, right, fit into the shell. So the first shell must always have only 2. So 2 here. Okay, taken 2 already. So you're only left with 11. So the second shell will fit 8. So you have taken 10. So the third one, or the third shell will fit the remaining. The remaining will be 3 electrons. So that means your 3 has to be on the third shell. Okay, and the last shell is called the valence shell, the outermost shell. The last shell, the outermost shell, which are filled with electrons, is called the valence shell. And this is most important because it actually determines the chemical properties of the element. Okay, so later on when we look at the chemical reaction, we're going to see this word valence. Okay, this valence is actually, it determines your chemical properties of the element. All right, so there's the outermost shell, which is called the valence shell. Okay, so now, if the question asks you to draw the electron arrangement, this is the answer that you should give. You must draw the respective shells. How many shells for you need to fit your number of electrons here. Okay, so here for aluminium, it will be 2 on the first shell, second shell will be 8, the third shell will be 3. Now, if we were to ask you to write, drawing is this one, drawing is this. If you write, you write this. This is called write the electron arrangement. If write is 2.8.3. If you were to draw, you have to draw in picture form like this. This is what you need to draw. Okay, what about atomic structure? If the question asks you for atomic structure, you need extra information. It is everything the same as your electron arrangement diagram, but with the addition of proton and neutron. You need to write, you need to indicate how many protons and how many neutrons in the nucleus as well. Okay, so now you learn 3 things here. If the question asks you for write the electron arrangement, writing means you just put in terms of number like this, writing. If you draw the electron, they want you to draw the electron arrangement, you have to draw the shells. Okay? You do not need to write how many protons and neutron because they only want electron arrangement. But if they want atomic structure refers to all 3. Atomic, remember all the subatomic particles, you need the proton, you need the neutron, you need the electron. That means you must indicate everything. You must indicate your electrons, you must indicate your proton, and also the neutron. Understand? All right. Okay, so this is what I've learned, taught you so far. Okay, now, lastly, all right, let's look at a concept called. Okay, so this is questions here. All right, if you want to do it, you should try the questions here. Just have a snapshot. Okay, do it on your own here. Right, isotope. Okay, before we end the lesson, let's go to one important concept which is called isotope. Now, what are isotopes? Now, just now I mentioned one important thing. They say that if the element is the same, right, it should have the same number of proton. Correct? So I said the same number. Okay, let's say for example, element A. Right, or element X, right? Element X, right? And element Y. If I tell you it has got it has got 16 proton. This one also got 16 proton. So what is your conclusion? Your conclusion here is these 2 should be the same element. So you cannot say element X, element Y. They are actually the same element because the proton is the same. Now, I said proton is the same, or actually, there could be variations in the number of neutron. All right? They are the same element, but sometimes some elements, even though they come from the same element, they're the same family, there are different members inside here, will have different neutron. So maybe this one has got 16 neutron, and the other member has got 70 neutron. See? So you have element this one and you have element this one. These are actually coming from the same family because they are the same element. But because they have different number of neutron, then we call these 2 as isotopes. Isotope basically means it's the same element. All right? It's the same element, but with different number of neutron. Okay, let's look at the definition here. Now, what are isotopes? Now, isotopes here actually, like I said here, as an example of a hydrogen. Hydrogen, actually, there are 3 types of hydrogen. Hydrogen element, there are 3 types of hydrogen element. Okay, even though they're all hydrogen, but they're actually 3 different members. 3 different members of the hydrogen family. Okay, let's call it that way lah. The element, the family is one whole family. All of them are hydrogen. All of them have a proton of 1. Okay, they have the same proton number, which is all 1. Okay, proton is down here. Proton is 111. See the proton number? All of them are the same. But you see, there are variations. Just like every finger of us, some are long, some are short. There are variations. Even though they are all from the same family, but there are certain variations. The variation is in terms of the number of the nucleon number. Okay, nucleon number is dependent on the neutron number, the number of neutron. Okay, later I'll show you, I'll draw the picture. So these are called isotope. These three are called isotopes. Understand? They are called isotope because they are actually members of the same family. That family is called the hydrogen family, which is hydrogen element. But they are just different in the sense that they have a little bit difference in terms of the neutron. Okay, let me show you the diagram. You show the diagram, you understand. Look at this. Right. Actually, hydrogen, right, is an element. Okay, let's look here. I'll put in red lah. There are three types of hydrogen actually. So look at the first one. The first one is H11. Now H11, as we've seen earlier, is 1 and 1. Here it means proton. This is the proton number. Proton number at the bottom. So I draw you here. The proton is white color. Proton ada satu, right? And on top here is also 1 because it has got no neutron. So P is 1 plus 0, no neutron is also 1. So it has got no neutron. Neutron I put black color. Okay, so this is what it looks like. It has only has 1 proton in the nucleus with 1 electron. 1 electron. 1 proton means 1 electron, right? Always the same because it's an atom. Okay, now look at the second family, second member. Second member is a little bit different. It has also got 1 proton because it's, of course, nitrogen, it must have 1 proton only. But you see here, you have got 2 here. Now, how to get 2? Proton is fixed already, 1. Hydrogen cannot have more than 1 proton. Otherwise, it's not considered hydrogen anymore. Okay, so it's 1 proton. So how to get another 2? 2 is because they are neutron. It has neutron. So you have 2 here. 1 proton, 1 neutron. So this is 2 here. All right, you can see this picture. This nucleus has got 2. This nucleus has got 1 only. With 1 electron, you always follow the number of proton. Okay, this is what hydrogen, the second one member looks like. Okay, we call it deuterium. Hydrogen 2 is called deuterium because 2, right? This is the nucleon number. Okay, the number at the back here actually denotes the nucleon number. Okay, now look at the third member. Third member is called hydrogen 3. Okay, H31. So here proton is 1. Again, proton only 1. But how to get 3? 3 is because there are 2 neutrons in the nucleus. Okay, and we call this hydrogen 3. This is also the nucleon number, and the special name is called tritium. This is hydrogen, which is a little bit different from the normal hydrogen in the sense that it has got extra neutron. Okay, so you can see here clearly that hydrogen not only got 1 type. Hydrogen, there are actually 3 types. But majority, the hydrogen that we found in this earth is actually this type. Okay, most of them are this one. The others are just minority. Okay, so basically not just only 1 type for every element. There are actually more than 1 type, and we call this isotopes. All right, let's look at it again. So what's the definition of isotope? Isotopes are elements which have the same number of same proton number but different nucleon numbers, or we can say different number of neutron. Okay, so not only hydrogen, look at examples here. There are more than 1 type of element we've got isotopes. Look at here, Si. Si is silicon. Silicon has got, you see, silicon Si 14. As long as the silicon, it will be the same number of proton number. But you see what's different? 28, 29, 30. This is the nucleon number. Okay, 28, 29, and 30. This is more, of course, the 30 has got extra neutron. Right? It has got 2 extra neutron. 29 has got 1 extra neutron. Okay, magnesium as well. Magnesium is 12. Proton number is 12. But you see the nucleon number? 24, 25, 26. Majority is this type. The rest, a little bit only, very minority will be the one which got heavier. The element has got extra neutron. Okay, Okay, P is phosphorus. Phosphorus, 15 here. 15 is the proton number. And the nucleon number, the normal one is 31. And there's one with 32. This is actually, this is called a radioisotope because it's, we call it radioactive. Okay, radioisotope are those which produce radioactive rays. So they call it radioisotope. And radioisotope, why do they produce radioactive rays? Because the nucleus is not stable. You've learned it in your chapter 8 when you talk about radioactivity, right? You see some elements which with the nucleus is not stable, it tends to undergo what we call radioactive decay. To become more stable, it will actually produce gamma rays, either gamma ray or alpha rays or beta. Okay, beta is actually electrons, all right, and alpha is actually proton. So they are radioisotopes. For example, this is phosphorus 32. We call it P32. This is radioactive, right? They are isotopes which are radioactive. Then they are used in the medical field and also used in research for investigative purposes. Okay, and you also see later on one of the uses of the radioactive is to kill bacteria and also to kill off the cancer cells in your body. Okay, these are the uses of some of the radioisotopes. So, all right, you can see the difference here. So, definition of isotope. Isotopes are atoms of the same element. So, they're actually the same element, same family, like I mentioned. Same family. Yeah, family is the word I use. I don't write that in your answer. You write same element. All right. Same number of protons, but different number of same number of proton, but different number of neutron. Okay. So there are other examples. Look at here, chlorine. Chlorine 35, chlorine 37. So isotope is named like this. How do you name isotope? You name isotope like this. You put the name and you put the number behind this, behind the name. The number actually refers to here. This is the nucleon number, right? Nucleon number. So this is actually the nucleon number. Okay, protons are the same. You can see very clearly. All right, electron also should be the same lah, because it follows the number of proton, right? And what's different is your neutron are different. Okay, neutrons are different. Okay, so next. Understand this? Any questions? Yeah. So how do you write your radioisotope? You write in this symbol Cl-35 or Cl-37. So this is the one which is radioactive. Normally the radioactive one I put in a asterisk to show that it has radioactivity. Okay. Same for carbon. Carbon also got 3 types. Not only carbon 12, you know. We always think carbon was only one type of carbon. Actually, there are more than one type of carbon. There are actually C12, C13, C14, and majority, more than 99%, of the carbon in the entire world, okay, is actually C12. With a minority of them are C13, and very, very little of them are C14, and this is the radioactive one. This is the radioactive element, which we'll use in carbon dating. Remember how we learned it? How do we find out the bones inside the ground that we dug up? How many years ago has the bone been there? Okay, how do we know this bone belongs to people who have lived 5,000 years ago? How do we know that? Okay, it's through carbon dating. Okay, you don't need to know detail yet, right? Okay, let's look at how do we find how heavy it is. We got relative atomic mass. How heavy is the mass of this isotope? Okay, so there's a formula to find out. Now, since we have got more than one type, okay, you got C12. Let me give you an example. C12, C13, C14. Actually, I mentioned majority is this type. So majority is this type. So that means the mass, we must take into consideration the average of all three. There are actually more than one type. You got 12, you got 13, you got 14. If you want to find the accurate mass, you must take into account all three. Okay, you must calculate and find out. Actually, the average is more towards the C12 because majority of the weight come from here. So, but that's a formula to find out. Okay, what is the relative atomic mass? Is it 12, 13, or 14? So actually, because 12 is the most, so we have to count by percentage. Okay, there's a formula to find out. Okay, let's look at this. How do we calculate the relative atomic mass given the different amounts of it? Okay, for example, chlorine consists of two isotopes. Okay, C35 and C37. The natural abundance, that means naturally occurring, how many percent is of the 35 type? How many percent is the 37 type? So it says that 75% is the 35 one. Okay, and the 25% is the 37 type. So that means this is majority lah. Majority is the C chlorine 35. The minority is the C chlorine 37. Okay, 这个是大部分，这个是小部分。In that sense, what is the average? Average cannot be 36. Average is not 36 because majority is more on this side. So we have to do a calculation. Okay, how do we calculate? There's a way to calculate. So you take the percentage. 75 is the percentage of the first type. You times 35 of the mass. The mass is 35 lah. Then you plus the 25% is the other type. 25 times the mass of it, 37. You plus it. Then you divide by 100. You will get the relative atomic mass of chlorine 35.5. That means we take 35.5 as the average of the two types. We cannot take 35 alone because there's also 37. And we cannot take 37 alone because there's also 35. Correct or not? So we have to take more or less like an average. All right? But because 35 is more, that's why you can see that the average is a little bit nearer to the 35. Okay, it's 35.5. So now we use the average. If the question asks what is the relative atomic mass of chlorine, it's 35.5. It will be given to you in order to solve the questions. Okay, it will be given to you. All right, okay, so this is the isotopes, and you will see that some of them are widely used in certain fields. For example, right here, you know, kill cancer cell. Now, you know, some people who have cancer, right, you have what you call a radiotherapy. Radiotherapy is how to treat illnesses or diseases using radioactive rays. That means usually it's gamma ray, because gamma ray is most dangerous. It's able to penetrate into the body tissues and is able to kill or alter the DNA of the cell. Okay, so it kills off the bad cells, or we call it cancer cells. All right. So in radiotherapy, we used to kill cancer cells, and the gamma ray comes from cobalt-60. So that means your cobalt-60 will be able to produce gamma rays. Okay. So iodine-131, all these are actually radioisotope. Okay, all of them are able to produce this alpha, beta, or gamma rays. Okay, why do they produce it? Because they want to become more stable. So like I mentioned earlier, all of these atoms or all of these radioisotopes, they are not stable. They are not stable because there are probably too many neutrons inside there. So in order for them to become more stable, it has to degrade, or we call it decay. So once it decays, it will actually produce all these invisible rays, which are the alpha, beta, or gamma, depending on what substance. For cobalt-60, it produces gamma ray. Okay. For, let's say, other elements, it could be only alpha or beta, which is less invasive, less dangerous. So it depends on what is the isotope. All right. So let's look at another example. Iodine-131 is to treat thyroid gland, which is hyperthyroidism. That means too much thyroxine is being produced, and also your thyroid cancer. Okay, thyroid is a part near your, what do you call this part? Your throat here. This is a gland here which produces hormone. Okay, yeah. This part is the thyroid gland. So it could be hyperthyroidism. Thyroidism means it's too active. It's producing too much hormone. Okay, next one. Phosphorus 32 is to study plant metabolism, to study especially absorption of fertilizer. Okay, whether this fertilizer is suitable to be used by this plant or not. You can measure see how fast this fertilizer has been absorbed into the plant, and we can trace it in the leaves itself. Uranium-235, you learned it in Form 3 right earlier this year, when you use it to produce electricity, to generate electricity. Okay, to produce electricity, to turn the turbine. Remember, it boils the water, it produces a lot of heat, it boils the water becomes steam, and the steam turns the turbine turns, it actually turns the generator, and it produces the We call it electricity. Okay, carbon 14. This is to estimate the age of bones that you dig up, the archaeologists dig up in the ground. Okay, lead 200 and 210, hydrogen 3. Now remember just now I told you the tritium, tritium, hydrogen 3. Okay, to study sewage and liquid waste. Sodium 24 to detect where is the position of the underground pipe that are leak, the botcher, we call leakage, or not pipe burst underground. Okay, so we need to know where it happens, so you don't have to dig up the whole street just to find where is the place where it is leaking. All right, okay, so these are the uses of isotopes. All right, so I've gone through a very basic concept that you really need to know. Okay, so my next lesson I'll go through relative atomic mass and relative molecular mass, so that you know how to do some calculation. Remember, calculation is very important in chemistry. Okay, if you cannot calculate, then a lot of questions are actually, in fact, I won't say all, but many of the questions are, in fact, the first 2 chapters you have a lot of calculations. So I'll guide you with that, with the calculation. All right. You have any questions? Maybe I can look at some questions. If you have any questions, yeah, we've come to the end of the lesson. Maybe we have any questions? You have any questions, anyone? If you have no questions, we will end the session. Yeah. Okay. All right, I think there are no questions. It will take about 10 to 15 seconds for me to read your messages here because of the delay in transmission. So I think there's no questions right here so far. So if there are no questions, then I'll carry on with another lesson another time, and I'll let you know where when, all right, so that you can follow and hopefully have a head start in chemistry next year, because chemistry, I see a lot of people are struggling with chemistry when they go to Form 4. Okay, so after going through my lesson, maybe you can decide whether you want to take chemistry or not. If you find that, oh, something I really hate this, I don't want to do all this, then you will help you to decide whether or not to take chemistry or not to take chemistry next year. All right, okay, so there's no question, I think. All right, so I will see you another time. Okay, so those who are new to my channel, if you have not subscribed to me, I will be helpful if you can subscribe, so that you will know when I go on live next time. You can follow the lesson. So I'll be just going a few more lessons, okay, before the school starts again. All right. All right. Okay. So no questions, right? Okay. I will see you then. All right. Bye-bye, students. Bye-bye, students. Bye. Nice to have you on my class. Bye.